or two?
Yeah, 2 minutes, I would say.
Okay.
At least I don't have emails from people who protest. Okay, so now we are on YouTube.
Okay. Nike, do you want to start sharing your slides, maybe?
Yeah, sure.
Yeah, that's great. There's some feedback. Okay, I think we should probably get started. So it's a great pleasure to have Nike-san and Alan Sly today, who's going to do a double presentation on the topic of statistical physics of randomized combinatorial problems. And we are going to start with Nike-san from MIT.
Okay, thanks a lot. So we will give the lecture in two parts. So I will give some more of the introductions. I will describe the type of problems that we are considering and some of the earlier results that we have on it, and then Alan will talk about some more recent work. Just to start with some examples of the problems that we study. Many of them are of this type, that where suppose that you're given a large finite graph. You can ask various computational questions about it. So does it have a proper coloring that involves some finite budget of colors, like 4 colors? Or can you find a large independent set? So an independent set is a subset of vertices that contains no 2 neighbors. So obviously it's more difficult to find the larger independent sets. And then it's interesting to ask what is the maximal independent set size that you can attain on a graph. And both of these are examples of constraint satisfaction problems. So in each of these problems, the constraints are imposed by the edges of the graph. So for the coloring problem, it says that the 2 vertices on either edge cannot have the same color. And for independent set, it's that they cannot both be occupied by the set. And then we will consider random CSPs, which are just CSPs of this type that are generated by some large random graph. And these 2 lectures are about sharp threshold phenomena and other related phenomena that arise in models of this type. So I'll start by talking about sharp threshold. So some examples that are known or that have been conjectured. So they were originally conjectured based on physics heuristics and also some numerical simulations. So these are some of the numerical works. And for example, if you take the Erdős-Renyi random graph in the sparse regime, so the average degree is D, then for any fixed number of colors, Q, it will be Q colorable with high probability if D is sufficiently small, and then not Q colorable with high probability if D exceeds some threshold D star. So this is still a conjecture, but there was a lot of progress made on this question in these works. Another example is that if you take the random regular graph, so this the uniformly random sample on the set of n graphs with degree D, then the maximum independent set size, if you normalize by the number of vertices in the graph, it converges to a constant limit that depends only on D. And this has been proved for large enough D. And then another example is that if you take an instance of random k-sat, so I will describe some related models, but if you take an instance of random k-sat where you have n variables and n times alpha constraints, then it will be satisfiable with high probability if alpha is small enough and unsatisfiable if alpha exceeds some threshold. And this was also proved for large K. And just some remark on historical background is that these types of models have been studied
Nike.
since, yeah.
Sorry, can I interrupt? There's a question in the chat asking what is Cue Colorable?
Oh, sorry, I didn't see the chat. So Cue Colorable means that you can assign a coloring of the vertices that uses at most Cue colors, which is such that no two neighbors have the same color. So it's easier to do if Q is larger. Yeah. Some background is that these models have been studied in some different communities since at least the 70s. So from the computer science standpoint, the goal is to understand, can you design algorithms that take advantage of the randomness in the model? So the algorithm would work in typical instances, but maybe it doesn't work in the worst case setting. And also, can you prove hardness in some average case sense? So not only is the worst case hard, but maybe there's some way to prove that the typical instance is hard for some model of computation. And what I will talk more about is these 2 points. So in the physics literature in the 70s, there were a lot of techniques developed to study mean field spin glasses. And then around the 2000s or late 90s, they were adapted to the study of random CSPs. And these gave a lot of very precise predictions about sharp thresholds and the geometry of the Gibbs measures and more than that. And the theory is very, very beautiful and unified, but it's not rigorous. And a lot of the goal of this work was to make parts of the theory mathematical. So I think from a probabilistic point of view, they're interesting because they're natural models where you have long range dependencies. And the easiest example of that is that if you just take a finite tree or any tree, it's colorable with any number of colors because the tree is bipartite. So certainly it's colorable. You just start from any vertex and you just assign colors going outwards, and you never make a monochromatic edge. But if you take the random 8 regular graph, for example, on n vertices, so locally it looks like a tree. If you take a typical vertex and you look in its finite neighborhood, it looks like the 8 regular tree. But it's also easy to just calculate. You can just calculate on this random graph what is the expected number of proper 3 colorings. And you would find that the expected number of such colorings is exponentially small in n. So with high probability, it's not going to be 3 colorable. So even though locally it looks like a tree, it's not 3 colorable. So it says that the reason that colorability fails in the graph, it's for non-local reasons. So for most of the talk, I'm going to discuss actually a variant of random k-sat, which is sort of simpler to study and is the one that we know the most about. And I'll describe the physics picture for it and start talking about mathematical approaches for it, and then Alan will take over from there. Okay, so for most of the talk, I'll focus on a particular model, which is a simple variant of the random k-sat model, which is easier to study. And it's easier to study because it's essentially a random regular graph. So this model has 2 parameters, k and d, which are both constant. And then the ratio, so actually we think of k as just fixed throughout, and then d is d is also a constant, but this ratio is a parameter alpha. And we take the bipartite graph, which is going to be degree k on the side above. So above are the constraints of the graph, and then below every vertex has degree d. So these are the variables. And it's arranged so that the number of half edges coming out from above is m times k, and this has to be equal to n times d, which is the number of half edges coming from below. So this implies this, and so then you take a uniformly random matching between the edges and then independently assign a plus minus sign to every edge. So you end up with a bipartite graph with plus minus signs on the edges. And this encodes an instance of the problem. And the problem that it encodes is the following. So this is one of the constraints. So these are the variables that participate in that. So we call it delta A. And the edges come with signs. So this is plus, and this one is minus. And the variables below have plus minus signs. And we say that the clause is violated if the three variables that participate in it, they take either the same signs as on the edges. So if they take plus, and minus, or they take the opposite sign. So if they take minus, and then plus. And these are the two configurations that are not allowed. And the other 6 configurations of these 3 variables are allowed. So that's a single one of the constraints. And then if you have a plus minus assignment of the variables below, which does not violate any of the constraints, then it's a solution of this instance. So I think in this picture that I drew, I chose it so that every clause has at least one of each sign. So that means in this example, if you take the all plus configuration, or if you take the all minus configuration, this would be a valid solution. And then, so since this is essentially a bipartite version of a random regular graph, it's sparse, and because it's a uniformly random matching, it will be locally tree-like. So when m and n are large, there will be few short cycles in this graph. So that's the model. And then the questions that we want to ask about it are, given an instance G, so given this random bipartite graph, it defines a solution space. So this is a set of all assignments of the variables which satisfy all those constraints. And this is a random graph. So this is a random subset of the discrete cube. And then we want to understand something about what it looks like. And then based on this spin glass theory, it was conjectured that there are a lot of phase transitions as alpha increases. So alpha is equal to the ratio between the constraints and variables, and it's also the ratio between D and K. So when alpha is small, it means that there are not a lot of constraints, and the prediction is that most of the solutions are kind of in one sort of well-connected block. So this is supposed to represent the discrete cube, and 2 solutions are close to each other if you can get from one to another by flipping just a few bits. And then the prediction is that after some threshold, the solutions become well separated. So there are large number of different clumps of solutions, and to get from one to another, to get from like this clump to this clump, you have to flip order and bits between any 2 of these clumps of solutions. And then there's a further threshold such that beyond this threshold, there are a bounded number of solution clusters. And this is a phase transition in the sense that the free energy will also be non-analytic at this point. And then finally, there will be a satisfiability threshold beyond which there will be no solutions. So this is the prediction that was made, and there are exact analytical predictions for these values of alpha. And there is some sort of notion of like, I'm not sure if universality is the right word for this, but I just mean in the sense that a similar picture, a similar phase diagram like this is expected for a few different models. So it includes random k-sat, random regular k-sat, random regular not all equal sat, and random not all equal sat. It includes coloring on random regular graphs or random Erdős-Rényi graphs, and it includes independent set on random graphs and random regular graphs. And this is maybe the one of the best references for this, for a discussion of this. So I won't talk very much about this, but I just wanted also to briefly mention that even in the unsatisfiable regime, so here where there are no solutions, it's also interesting to study these problems. And here the natural thing to do is to look at the Gibbs measure, which is defined by this Hamiltonian. So you can take, for any assignment of the variables, just take the number of constraints that are violated by it. So H is a random function on the cube, which is determined by the problem instance. And then this mu is the Gibbs measure, which is determined by the instance. And as you send beta to infinity, then it will concentrate on either it will concentrate on the solutions of the problem if you're in the satisfiable regime, or if it's not satisfiable, then it will concentrate on the max set configurations, which are like the ones that violate the smallest number of constraints. And this relates to problems in, I mean, the max set problem is also much studied in computer science. And in this regime, you can ask, what does the H landscape look like? So, or in other words, what does this measure look like? So is it concentrated in sort of a constant number of clusters, which is what is expected before satisfiability? So is it like a similar picture after the threshold? Or is it something more complicated? So this is sort of a picture of what we understand roughly about this model. So there's a lot known up to this non-analytic point by earlier works. And then we also know how to compute this threshold and how to compute the free energy beyond this transition. And it's known what the satisfiability threshold is. Beyond the satisfiability threshold, a lot less is known. So the conjecture is that this type of behavior continues for a while. And then it's known that at some point beyond that threshold, it can no longer be a simple behavior like that. So this is roughly what is known. In this talk, I'm going to focus mostly on this threshold, how to compute it, both non-rigorously and how you would try to prove it. And then I think Alan will focus on this regime. Okay, so now I'll switch to a more handwritten notes. So this is just a review of the problem I just described. So again, this is the problem instance, and then we look for an assignment plus minus of the variables which satisfy all of the clauses. So I will let S denote the set of all solutions of the instance. So this is a random subset of the discrete cube. And then I will let Z denote the number of solutions of the instance. So if we want to know the satisfiability threshold, we just need to understand when this random variable is non-zero. And then also, ideally in the satisfiable regime, we also want to know something about the free energy of the model. So I'll spend a little time to just describe the physics approach to this problem. So there are two approaches which are well known, which are the replica method and the cavity method. They give equivalent results in this model. But I will describe the cavity method here. And the basic approach, it's very simple, which is that you have this random graph Gn, which defines your model, and you can think about it that you build a random sequence of graphs Gn, such that each GN is a sample from the model that you're studying. So each GN is a sample of random regular not all equal set. And then they give and then GN plus 1 has only a few differences from GN. And then if you want to know the number of solutions of GN, you can try to estimate it by this telescoping sum. And then hopefully each of these terms might not be very difficult to compute if GI and GI minus 1 differ only a small amount. And one thing that you might imagine is that when you go from GI minus 1 to GI, maybe the ratio of the partition functions, it will concentrate around some constant value for most of the steps that you take. And in that case, this constant value would be the free energy of the model. So another possibility that also can occur is that maybe each of these individual steps, there's a lot of randomness. So maybe each of these terms is random. So they don't, each individual term doesn't concentrate around one value, but when you take a product of a lot of roughly independent steps, then the product will concentrate. So that's the other possibility that we can have. So that's the idea of the cavity method, but it can be complicated to obtain the right value that it concentrates around, even heuristically. And this is sort of part of the challenge of implementing the cavity method correctly. So the general scheme of the cavity method is that you start from your graph GN, you delete some stuff, you get a cavity graph, which is some intermediate graph. Then you add some more things and you end up with your GN plus 1. And you can do this for a lot of different models, and the addition and deletion steps, they will depend on the particular model that you have. And then you have to be just a little bit careful to make sure that every GN that you have is actually a sample from the correct distribution. So I'll describe roughly how it goes for a random regular not all equal set. So it's easiest to describe if d over k is an integer, but this doesn't really matter. But if d over k is an integer, then you can do like the following. So Gn is the one instance with n variables. Then you delete a random subset of clauses. You delete alpha k minus 1 of these. This gives you the cavity graph. So here this entire thing is Gn. I choose at random these clauses and I delete them and I end up with the cavity graph. So these variables here are special in the cavity graph because they were neighbors of the deleted clauses. So all of the variables in the graph have degree d, except for these variables which have degree d minus 1 in the cavity graph. And then given the cavity graph, you add back in a new variable so that you will have a total of n plus 1 variables, and then you connect it to the previously the cavity variables. You connect them up with the correct number of clauses. So those are the two steps, and you re-randomize the signs on the edges. So you assign new plus minus signs. So throughout, I will use capital U for these special variables, which are neighboring to the deleted clauses in the Gn, and then are also neighboring to the additional clauses in Gn plus 1. So if you, so then we want to calculate how the total number of solutions changes when we go from Gn to the cavity graph to Gn plus 1. And this is, it's easy to write down what it is. So if we let mu cavity n be the uniform measure on solutions of the cavity graph, then the ratio between the number of solutions on Gn divided by the number of solutions on the cavity graph, it's exactly the same as the chance that random solution of the cavity graph will satisfy the clauses that are in GN, but not in the cavity graph. So this is not an approximation, it's just an exact equality. It's just a way of rewriting it. And similarly, the partition function on the GM plus 1 divided by the partition function on G on the cavity graph, you have to sum over the plus minus spin on the new variable. So this corresponds to plus or minus here. And then it's a chance that a sample from the cavity measure together with this new spin will satisfy the new clauses that are in GM plus 1, but not in the cavity graph. So these are both just.
Can I interrupt again? There's another question about whether the graph is bipartite or not.
That's right. The graph is bipartite. So the variables, like a variable never neighbors a variable. So a variable always neighbors clauses only, and clauses also, they always neighbor only variables.
Okay.
And the clauses express the constraints. So these are both exact equalities. And then the hope is that you could calculate them because this is just a sum over plus and minus, and then U is is a finite set. So the size of U it's a constant D times K minus 1. And the only problem is that in order to evaluate these, we have to know what is the joint law of all of these spins under the cavity measure. So if you sample a solution from this graph, what is the joint distribution of those variables? And clearly this is the problem for evaluating these ratios. So in this particular model, we do know a little bit more, which is that if you have a single variable v, then we know that under the cavity measure, it will be 1/2 plus and 1/2 minus. And this is just because in this particular model, it's plus minus symmetric. So X is a solution if and only if minus X is a solution. So the solution space is invariant under flipping the sign. So in this particular model, you do know that for a single variable, it's uniformly distributed. And then, so like I said, the graph is locally tree-like. It doesn't have a lot of short cycles. And this means that the variables in U, they're typically very far apart from one another in the cavity graph. And then the most natural guess that you would make is that they should be roughly independent under the cavity measure because they're far apart. So it's reasonable to guess that the cavity measure has some kind of correlation decay. So things that are far apart should be roughly independent. So this is the replica symmetric assumption, which is that the joint distribution of the cavity variables is roughly equal to just the product measure. And here in this particular model, we know that each of these is just 1/2. So it's just the uniform measure. So if you assume that, then of course that means you can calculate these ratios because instead of the cavity measure, you just put the uniform measure. So it's a chance that a uniform configuration satisfies the new clauses. And this is just exactly 1 minus 2/2 to the k to the number of clauses. So this is a chance that a uniform configuration will satisfy a single clause. And likewise for GN plus 1 to the cavity graph, it's roughly 2 because this is for the sum over the xn plus 1, and then the chance of satisfying a clause raised to the number of new clauses. So this gives a prediction that the ratio between GN plus 1 and GN, the number of solutions will be roughly this value. And this is the replica symmetric free energy as calculated by the cavity method. And so this concentrates around a single value for each step of adding a vertex. So then it would suggest that the partition function should just be this to the power n. So this is a replica symmetric prediction. And in fact, it's known that this prediction it is correct for a fairly large range of values of alpha. So it's correct for alpha up to this value, alpha con for condensation, but it will fail strictly before the satisfiability threshold. So in particular, the satisfiability threshold, it's not going to be given by just the point where this will cross zero. So so it says that alpha sat is not equal to I guess log 2 divided by because it will be incorrect before the satisfiability threshold. So what happens when the replica symmetric prediction fails? So then with high probability, what happens is that the number of solutions is very small relative to the replica symmetric value. And also the cavity measure, it's not what we would have expected. So it's not just the product measure or the uniform measure. So this means that the cavity method has long range correlations. And in this regime, physicists proposed an explanation for these long range correlations. And the proposal is that they can be explained by a one-step replica symmetry breaking structure, which means in this context as follows, that most of the solution space of the cavity graph, the idea is that it decomposes into components or clusters, gamma. So this is again the discrete cube, and this is like a clump of components. So it's some connected component inside of the discrete cube, such that if you take the uniform measure on solutions, but then you condition on being within a particular component, the conditional measure has correlation decay. So meaning that the conditional measure is replica symmetric, even if the overall measure is not replica symmetric. So then when you go to try to calculate this cavity quantity again, what you shouldn't immediately approximate the cavity measure by a product measure. So instead you can decompose according to which cluster you are in. And then once you condition on being in a particular cluster, then you can approximate by a product measure within that cluster. And then you would be able to calculate this quantity, except I didn't explain how to derive some of these things. So I didn't explain how to get the cavity measure, how to get the marginals of the measure within the cluster. And I also didn't explain what is the decomposition into the clusters. I think Alan will talk more about this, but if you believe that you have some way of computing this measure and you have some way of computing these marginals, then it would give you this ratio. And similarly, you would be able to calculate the ratio from GM plus 1 to the cavity graph by first decomposing into clusters and then doing a product approximation like before. And then if you take this and put it together, then you would get a different value for the free energy. And this value is the 1 RSV free energy. So it comes from, you can get it by doing the same cavity calculation, but you have to decompose the cavity measure before the product approximation. And it is strictly smaller than the replica symmetric free energy once you're above the condensation threshold. And we proved in this work with Alan and with Yumeng Zhang that this is correct up to the satisfiability threshold. And the satisfiability threshold, it's given by the point where this function will cross zero. This is proved in an earlier work. So up till now, these are all heuristics. And for approaching how to prove these results, actually we rely on more of a combinatorial picture for what is the structure of the cavity measure. So I'm going to describe now the combinatorial view on this measure. The combinatorial view, it's also the way I describe it. It will be like a heuristic, but actually the proofs go directly starting from that heuristic. You can build the proof from there. So okay, so I want to describe a model for what this cluster looks like. So again, a cluster is like it's a subset of the solutions of the instance. So it's a subset of the discrete cube, and it's connected, meaning that from you can go from any solution to another solution by just flipping a few bits at a time. So just to be simple, we will say you can flip. You can get from any solution to another one in the same component by flipping just one bit at a time. So why do solutions tend to cluster? And this is simple to understand because in this model, each variable belongs in just a bounded number of constraints. So each variable is only constrained by d things. And so then typically it will happen that there will be some variables that are just not really constrained. So for example, the situation here is that if you look, for example, at this constraint, so this is a plus edge, this is a plus edge, and this is a plus edge. And here I put a blue dot to say that this variable takes a value plus, and this variable is yellow, takes a value minus. So that means that whatever value this one takes, this clause is already satisfied because it has one variable which evaluates to minus, and it has one variable which evaluates to plus. So this clause doesn't care what value the variable will take, and it's the same for all of the clauses around it. And so it's clear that if you have a random graph like this and you look at a typical assignment of the vertices, it's easy to imagine that you should have some positive fraction of variables which are just not constrained by their neighbors. So we call these free variables, meaning you can flip them without violating any of the constraints that they are belonging to. So if you have a positive fraction epsilon of variables that are free, then it suggests that a typical solution X will lie in a cluster of solutions of size something like 2 to the n epsilon, because you should be able to flip all of these independently, more or less. So it's not exactly correct, because you might have two neighboring free variables that might interact in some non-trivial way. So this is an example where both of these variables individually are free. You can flip this one without violating any constraint. You can also flip this one without violating any constraint. But because they share a clause where this is minus and this is minus, you can't flip both of them at the same time. But so this can happen, and it will happen, some positive fraction in the graph. But the occurrence of this type of interaction, it's pretty rare. So the real cluster size, it should be something like n epsilon, and there will be some smaller correction to that. So this is just repeating what I just said, that the structure of the solution cluster, it's not trivial, so it's not like just a subcube, but when k is large and alpha is fairly large, so alpha is somewhere in the range of the satisfiability threshold, we claim that the cluster structure is still pretty simple. So it's not like as simple as a subcube, but it's not much more complicated. So say that this is a cluster, it defines this free subgraph. And so these are, all of the green are like the free variables. And outside of the green are variables that are just frozen. So most of the variables will be frozen to either always plus within the cluster, or they're always minus within the cluster. So any solution in the cluster is always plus here, or it's always minus here. Sometimes so among the free variables, most of them are just isolated vertices. So it's a single vertex which is surrounded by frozen neighbors, but you can flip the value of this variable and it won't violate any of the constraints. And sometimes you have like a linked pair of free variables, so that would be like this situation here that I described. And then sometimes you have some bigger tree of linked things. So roughly, if you do like a kind of rough calculation, it's something like the total number of free variables is like n over 2 to the k. The total number of free pairs is something like the square of that, maybe times poly k, and so on. So this free subgraph, it looks like a very subcritical percolation on the graph, very, very subcritical. And as a result, most of the components are going to be just trees of bounded size. Sometimes, like very rarely, you might get some more complicated subgraph, but the total occurrence of these will be like of constant order, and they can be just dealt with separately. So it's a pretty simple structure, and note that two variables within a cluster, their values would be correlated only if they're in the same free component. So most variables are just in the frozen region, so their value is just completely fixed. And then some variables, they can be plus or minus. So they can be plus or minus, but this variable is clearly not dependent on any other variable. So the only situation where you have dependence is when you have like one variable here and one variable here, and they're dependent on one another. So this is like kind of a heuristic argument for why you expect the measure to have correlation decay, because it has correlation decay for a very simple reason, which is that variables which are far apart are not going to be in the same tree component. So they will be independent of one another. So this is kind of heuristically supports this one RSV idea, which is that the within cluster measure is replica symmetric, because the within cluster measure, it has this kind of simple decomposition, even though the overall measure on all of the solutions might not be. So this is kind of a combinatorial explanation of what one RSV means in this model. So then, in order to try to compute the satisfiability threshold, if you only care about satisfiability and not about how many solutions there are, then it's enough to just count the number of clusters. So the total number of solution clusters is a good proxy for whether there are solutions. And it's useful to have a combinatorial encoding for what a cluster is. And one good encoding for it is that you can represent it as just a plus minus free configuration where eta satisfies the following rules. So it's plus or minus if and only if it's forced to that value by one of its neighbors, and otherwise it's free. So this is just the rules of a model involving plus, minus, and free on the variables. So you have to be a bit careful, because not every eta which satisfies these rules actually corresponds to a real cluster. Because if I could take eta to be free everywhere, and this does satisfy the rules that are imposed by this model. But if you just put eta equals free everywhere, that it doesn't correspond to an actual cluster. But it's possible to prove that there's approximately a bijection between actual clusters, gamma, so actual connected components in the space of solutions. It's roughly in bijection with configurations eta, which are plus minus free, which satisfy these rules, with the additional constraint that the density of free variables has to be pretty small, so roughly 1 over 2 to the k. So this is some like more complicated set that we want to study, but we can study it via this kind of simple model of plus minus free encodings. So for this model, you can also do the whole thing again with the cavity method and replica symmetric approximation for the uniform measure on these things. So now it's a uniform measure on some subset of this space rather than plus minus to the n. But of course, then you can do similar calculations. And then it would give you instead of the number of solutions, you take the ratio of the number of clusters and you get some different formula. And then the satisfiability threshold, if this formula is correct, then it should be given by the place where this function crosses 0. So then just a comment on how you would do that. So how to actually calculate this thing. This calculation also relies on this combinatorial encoding. So this measure, it's on the one hand, you think about it as a uniform measure on the space of clusters. So each cluster is weighted as 1 or has equal weight under this measure. But of course, it's easier to study it as a uniform measure on some subset of the plus minus 3 to the n. And then the product measure would be each individual marginal is just some measure on 3 values plus minus 3. And also by symmetry, the plus and minus would have the same weight. So all you need to do is make sure that you know what is the value of the free spin. And this has to be solved for, but because it's replica symmetric, you can approximate it by a tree and solve a tree recursion. So you can solve some tree recursion. This will give the value of the free spin. And then once you substitute it in, it will give you this ratio. And then you take the 0 of that, and that will give you the satisfiability threshold. So there's some step that I won't really describe where you solve a tree recursion, but it's relatively simple. So I put a derivation, but I think maybe I will skip this part. And so that's the heuristic for it. And the proof approach is very close to this heuristic, which is that the method is essentially to apply a moment method on these encodings. So morally, you're doing moment method on the number of clusters rather than the number of solutions, because the number of solutions is not well concentrated. And in order to do moment method on the number of clusters, it's easier to work with these encodings, which are in the plus minus free spins. And a similar approach was explored first by this work. So in an earlier work, we took this approach and found the satisfiability thresholds for this model. And then we have there are some later works that are satisfiability threshold for a different model, and also the 1 RSV free energy up to the satisfiability threshold. This is a work that Alan will talk about, which is in the regime that leads up to the satisfiability threshold. And in a work that I won't have time to talk about is the satisfiability threshold for random K-sat, which is, it's more complicated in that each step of the cavity calculation, it doesn't concentrate on a single value. So the steps of the cavity method give random values, and then there should be some averaging. So that makes it more difficult to study. But I would say that all of these works, they have kind of the same starting point of encoding the clusters in some combinatorial way, and then trying to work from there. I think I've reached the end of my time, so I'll stop here. Thanks a lot.
Thank you. Are there some questions? You can either unmute yourself or ask in the chat. I mean, I have a very general one, but you know, I'm a bit ashamed because it's probably super naive and a bit ignorant. But I was wondering if you can say something about the process of the set of solutions as you vary the parameter, as you vary alpha. Can you think of this in a dynamical way?
Oh, yeah. I would say probably the technology is not there to study any refined question about that. Yeah, I don't think you know, all of the works are like, it's like sufficiently difficult to prove kind of first order asymptotics about these models. So I haven't seen anything that considers it from a dynamical point of view.
I see. Okay. Okay. Are there any questions beside this very naive one? So if not, I propose that we all unmute ourselves to thank Nike again. And we should take a small break. Maybe we start again at on the hour. Is that okay, Nina?
Yeah.
So we have a 8-minute break and we start again on the hour.